Here we are for the short video overview of Unit 2. So here we can see the main highlight is to perform expectation, design a solution for a complex real-world problem by breaking it down into smaller, more manageable problems that can be solved through engineering. All right, how do we contextualize that? There's a lot of skill development in this unit. So after a hook from the health teacher, if you can get them, they're almost always interested in having students look and use STEM to enhance a social discussion. You know, what are the distances? Parking lot versus freeway, texting and driving, distracted driving. All right, so I'm going to just go forward with it that this is that physics teacher's kind of dream, right? You got this big complex problem. So what do you need? You need to draw a picture. You need to think through. We call that system analysis. Think through what you know, what you need to know. And we even have it scaled up to the fact that they might need to know an equation to solve something. So they got to construct a mathematical model from an experiment. And then they're going to use that mathematical model to code an app, a spreadsheet simulation of texting and driving. And then it culminates in them using their own simulation that they got the equations to code it from labs they performed and make an argument from evidence, where their evidence, as I just said, is of their own creation, which is so different than social studies and language arts, where they're always oftentimes citing other sources. All right, so you can scroll down the website. So I'm going to just hit a couple highlights that are buried on that page. All right, so there's that request for health teachers. Here's an example email right below to make that a little bit easier for you. There is, of course, several videos. There's a long one. And then once they get good, you can switch over to the short graphics. There's even, or a short one with graphics. And want to just point out that after some brainstorming on a whiteboard and a sheet of paper, we want to kind of funnel them to get close to this one. Why? Because then when they actually code their spreadsheet, they just see the similarities. And it allows them to be successful in that first major spreadsheet that they do. It's thrilling. This is, you know, students feel like they've really learned a career connected skill. All right, so that's the system analysis. And as we already mentioned, they realize that they need some equations. And so how do we get them? Those are in patterns in the data. So one last thing, though, to just say is stronger, clear. We really want that system analysis to drive the learning. So they got to be good with it. And we don't get to do this too often, but stronger, clear, you know, student explain, you know, in 60 seconds, 90 seconds, explains that whole thing, that they get a compliment from B. B reciprocates and gives a 90-second explanation, gets a compliment, and then you mix the students up and do it 2 more times. Everyone groans, even summer teachers at the summer workshop do it, but everyone at the end is like, oh my gosh, I really get this now. That is such a good feeling. We want students to have that. And that allows that system analysis to drive the learning. All right, so then in our storyline, what haven't we done yet? They've done tons of speaking, writing, interacting, and listening, but they haven't read. And we need to find out how good breaks are. So right from the Oregon Driver's Manual, again, there's text, there's graphics, and there's some key information they got to get breaking. They'll put that back in, you know, and sorry, I skipped over a couple things here, but velocity of the car we get from the video, time of distraction. There was many experiments that I skipped over. I went all the way down. We're all the way down to here. The deceleration due to braking we got from the reading. Now we need to find the time of braking. And I'm going to, again, so here we're at the finding models in between computational thinking. And again, I'm just jumping in on the short video. And they just play with it, graph literacy. So they just see as you speed up, the time of braking goes up. That's no surprise. Every student could do this. As your brakes become more powerful, the time slows down. And you can do some easy numbers, but in any case, they figure out what mathematical model pulls that off. They put that in their system analysis, and we're moving on. So we have that last one of how far does the car go while braking? Well, we start simple. What's the simplest acceleration? Speeding up from rest. Want to just point out that they hypothesize now. We're at past unit 1, so they know it's horizontal line, proportional, quadratic, or inversely proportional. They can eliminate horizontal line and inversely proportional. Now they're down to proportional and quadratic, but they know constant velocity is proportional. So they have a really good chance of hypothesizing that it's quadratic. They might need to be primed to think through this, but that's what we say, confine the playground to those 4 patterns. And then students that hypothesize that have their brain set up to learn it. So that's pretty exciting. This does have that card sort, super powerful. This is where a lot of it comes together on the card sort, and then a peak right after they finish the card sort. Yeah, they really start to say, what is that constant? Oh, it's the number in the mathematical model because it was always the same. On the graph, it shows up as, oh, the curvature of the line. And in the real world, it is the acceleration. We know on a steeper ramp, it had a bigger number. Sometimes they think it's steepness of the ramp, but we took data on the ball. What does the ball have because it's on the ramp? Oh, it's going fast. Yes, but they all eventually go fast. So a high ramp goes fast, faster. It gets going fast, faster. That's acceleration. There is a 1/2. Our suggestion now, after a lot of discussion, really is save something for junior, senior year. It is okay to go ahead and tell them it is 1/2 acceleration. There's a reason, and you could give it in 60 seconds. We used to have them construct it, but that takes a whole extra day, and you'll want that day for Unit 6, climate change and electric guitars. All right, then moving on, here is a graphic organizer for the conclusion. This is that chance to really, we're in Unit 2. This is the last one where it's like this for all students. We're going to start pulling back this scaffolding. All right, moving on though, we did do some more thinking, computational thinking and spreadsheets to figure out, hey, what happens if you are on a bus that's going to constant velocity plus you're accelerating? Oh, it's going to be the 2 together. How far the bus moves and how far you move inside the bus because you're accelerating. All right, with that, we have everything we need. We can now code it. And again, just look at how similar those two are. And I want to just say that there's 3 levels of support. So think about what level, managing both the time and the appropriate challenge. So ideally, the lowest level of support for students to be successful, but just know there's customized videos for all 3 levels of the support. And now that they've made their simple one, they might have said tired or icy roads and all of these things. That's good stuff, but we started simple, so we could come back to it and iterate the app. I was going to just show that. I was going to jump all the way back here. Hey, if you drifted into oncoming traffic, you would need to change the velocity to the velocity of the car approaching the truck. And so this 10 would turn, if they're each going 10, they would be approaching at 20. It auto changes. That is the power of computational thinking and starting simple. Now we can go back. Oh, you're tired? Change the reaction time. I should add sleepy and maybe it's 1.6. You can see it. So now that we have this, we can really think through a lot of different scenarios quickly. Computational thinking, a human brain plus a computer. Very powerful. All right, so to wrap it up, they got their simulation, they've learned something about it. Now they're going to use that to argue from evidence. And how cool is that? Their CER is referencing evidence data from a simulation that they coded from experiments. And they then go on to a new scenario. This student picked drunk driving in addition to distracted driving. And then it ends on what are the impacts of science on society. So really nice, something we always want for students, but don't often ask them to write about it and give them feedback. All right, then writing is always difficult, but it's so important. It organizes the mind. It's really helpful for a lot of students to actually learn it. But of course, that's hard. So there's a lot of supports and there's some extensions for the students that don't need extra support. You can keep them productive learning by modifying that app. It was all in meters per second. So many students think in miles per hour. Build a converter. All right, with that, here's the end overview of the short overview of Unit 2. How do we use STEM to enhance a social discussion?